Okay, so today we're going to talk about derivatives, and there's actually quite a bit of good news here. And the good news is, what you're going to notice is derivatives is just another way of pretty much saying what we've been doing in section 7. So you'll notice that there's a lot of similarities with section 7 here, which that's fine. It's just to introduce you to new vocabulary. So when we say derivatives, you'll notice that instantaneous rate of change or the slope of the tangent line, they all pretty much represent more or less the same thing. So let's kind of start off by recapping from last section. So we said that last section we saw that the slope of a tangent line to a curve and the velocity of an object given the position function were the same. Right? I mean, that was kind of like what we saw. We saw that, look, last section we said, how do you find the slope of the tangent line? And then we came up with an approach to doing it. And I'll give you that in a minute. And then we said, okay, well, what if that function represents the position function? How do I find the velocity or instantaneous velocity of that object? And then we said, well, it was the same thing that we did when we found the slope of the tangent line. So if you remember, we said the slope, I mean, when I say if you remember, you better remember, right? Because it was just literally a day ago, and we don't learn things to forget them anyway. So if I have m, we described it as limit as h approaches 0 of f of a plus h minus f of a all over h, right? Where a is the x value in which we're finding the slope of the tangent to that curve. And we said v of a, which is finding the velocity of the object at a given time, let's say, and the time is a, is described as limit as h approaches to 0 of f of a plus h minus f of a all over h. And if you look at this, they're the same thing. The only difference is this function here is just a function. We don't know exactly what this function represents. Whereas this function here, f, represents the position of the object at each given time t. So that's the only difference. Other than that, they're practically the same thing. So what we could say is that, in fact, this type of limit has a name. So this has a name. And this is what is known as the derivative. So let's actually define what the derivative is. So the derivative of a function f at a number a denoted by f prime of a is, so let's just stop here for a minute. Anytime you see f with kind of the apostrophe, this means f prime of a. This is what it's read as, okay? So this means f prime. So in other words, we're saying find the derivative of f at the number a, okay? So kind of like, we'll see how this ends up being the same thing as the slope of the tangent or velocity in certain instances. So here's how we're defining f prime of a. f prime of a, in other words, is equivalent to the limit as h approaches 0 of f of a plus h minus f of a all over h. So if you notice this, this is actually the same thing as you saw last section, right? Except instead of calling this m, we're calling it f prime. So if you remember in section 7, we called this m, which was the slope of the tangent. So basically, from this point on, you'll see this notation, f prime of a, which is basically doing the same thing as finding the slope of the tangent to this curve f at a. And it's also known as the instantaneous rate of change of f at a, and it's also known as the derivative of f at a. So notice how basically we're saying the same thing in different ways. Okay, so if I say, what's the slope of the tangent line of this curve at a? That's the same thing as saying, what's the instantaneous rate of change of f at a? And it's also the same thing as saying, what's the derivative of f at a? Okay, so, and in fact, that's probably the quickest way of saying it. So of course, granted that if this limit exists. Okay, so don't get confused by the wording of things, because we're pretty much saying the same thing over and over and over. Okay, so let's look at our first example. So for example 1, we are going to say find the derivative of f of x equals to x squared plus 2x minus 3 at the number a. And see, now we're just generalizing it. We're basically saying, in other words, we're saying find f prime of a. Okay? And see, I like it better when we generalize it, when we say at the number a, because we're keeping this kind of like a variable in some sense, right? So for example, once I find this, then I could say, okay, what's the derivative at 2? Well, then if you have this in the generic form, you can just plug in 2 for a. And then you could find it at 3, then you could plug in 3 for a, and so on. So by definition, what is it that we're doing? We're saying f prime of a equals to the limit as h approaches 0 of f of a plus h minus f of a all over h. So now we can go ahead and plug these in. So I'm going to go to the next page. So that equals to the limit as h approaches 0 of f of a plus h will now turn into a plus h squared plus 2 times a plus h minus 3. So if you remember, this is actually, all of this is my f of a plus h, okay, including the negative 3, okay, minus f of a. And anytime we say minus f of a, I put parentheses around the f of a, just so we understand that this negative needs to distribute to every term for f of a. So this will just be what? A squared plus 2a minus 3 all over h. And if you remember, just like section 7, we just need to simplify this, and everything that doesn't have an h on top better cancel out. Because once they cancel out, then I could factor out an h from the numerator and cancel with this denominator, and then I could evaluate this limit, and that means my derivative exists. So then what do I get? I get limit as h approaches 0. And let me make a comment here. I know some of you are already forgetting this. Remember what I said. Don't forget to include the limit in every step. The only time you could remove the limit is once you use the direct substitution, if we could even directly substitute. So let's simplify this. What's a plus h squared? That's going to be a squared plus 2ah plus h squared. Distribute that 2 plus 2a plus 2h minus 3. And then if I distribute this negative, it gives me minus a squared minus 2a plus 3. All of this divided by h. Okay, so now let's start the canceling process, which here's where the fun part begins. A squared minus a squared, gone. 2a minus 2a, gone. Negative 3 plus 3, gone. And what do you know it? What we have left is everything just in terms of h. So this is 2ah plus h squared plus 2h. All of this divided by h. So now I could factor out an h from the numerator. If I factor out an h from the numerator, I get the limit as h approaches 0. Factor out the h, that leaves me with what? 2a plus h plus 2 divided by h. So now we could cancel out the h's, and now we have limit as h approaches 0 of 2a plus h plus 2. And now I could use direct substitution. And now that I'm going to use direct substitution, now I could drop the limit. See, notice how I always write the limits out. So then this becomes 2a plus 2. So in other words, what are we saying? F prime of a equals to 2a plus 2. Now remember, why do I like this? So we're done with this example, by the way, but let's kind of talk about this. Why do I like this? Because if I ask you now, what is f prime of 1? Instead of having to do all of this work all over again, you can just say, well, if f prime of a is 2a plus 2, then f prime of 1 is just going to be replace a with 1, and then you get what? 4. And f prime of 2, then you can keep going. So I prefer this as opposed to finding f prime for each number. So I prefer this over anything else because then you can answer multiple questions here. Okay, so let's move on to our next definition here. So now we're going to define how to find the equation of the tangent line. Now you'll probably say to yourself, wait a minute, didn't we define how to find the equation of the tangent line last section? And the answer is yes, except now, since we could express the slope of the tangent line in terms of derivatives, we're kind of going to reword this in terms of derivatives. Okay, so let's actually define it right now. So the tangent line to y equals to f of x at the point a comma f of a is the line through the point a comma f of a whose slope is equal to f prime of a, which is also known as the derivative of f at a. Okay, so once again, this is saying the same thing as last section, except instead of f prime of a, we just called it m, which is defined as limit as h goes to 0 of f of a plus h minus f of a all over h, which this is saying the same thing, except now we have better notation for it. So from this point on, we're probably going to deal with derivatives more than just calling it the slope of the tangent, because the derivative has so many representations. Okay, so now let's also define something else. In fact, yesterday we said the slope of the tangent line means 3 different things. So the derivative means the slope of the tangent, but the derivative also means instantaneous rate of change. So if you remember, the slope of the tangent of a curve gave us the instantaneous rate of change. So for example, if I were to draw a picture off to the side here, if I have this curve, see at this point, the derivative, which is also the same thing as the slope of the tangent, it tells me at that instant how fast this curve is decreasing by, which is known as the instantaneous rate of change. So by definition, what we know is the derivative f prime of a is the instantaneous rate of change of y equals to f of x with respect to x when x equals to a. Okay, so in fact, for homework, they're actually going to ask you to explain in words what's happening. Okay, so just be ready that, for example, if you find a derivative of a function at some value a, what you're going to say is, in the way of describing this, what is it that we're going to say? We're going to say, look, when a of this, whatever this is, if, like, let's say you're producing some units, you'd say when a units are produced, then the derivative at that a, when the a units are produced, tells you how much the production is increasing or decreasing by when a units are produced. So it's kind of like, it's at that instant, it tells you how much your production of something, whatever it may be, is increasing or decreasing per unit when you make a units of that product. Okay, so like, let's say, for example, if I give you something like this, f prime of 9, where let's pretend that this has to do with how many cell phones your company is producing, and f prime will give you how many units of cell phones are increasing, how many of the units that you're making are increasing or decreasing. So let's say if I'd say this, 10. What does that mean? If you make 9 cell phones, if you produce 9 cell phones, the rate of the number of cell phones that you're producing is increasing at a rate of 10 units, or it's increasing at 10 per unit. So that means, for example, if I make 9 cell phones, then at that instance, the number is increasing. And in fact, that probably doesn't make sense. If I were to change it to 2, what would that mean? So the moment I make 9 cell phones, the rate in which the number of cell phones I'm producing is increasing at what? 2 cell phones at that instant. Okay, so that's kind of what it's telling me it's doing here. So let's move on. So for example 2, we're going to say find the equation of the tangent line to the parabola y equals to x squared at the point 2, 4. Okay, so here's what we know. We already have the point of tangency. And so what is it that we want? We want to find the slope of the tangent line at this point 2, 4. So in fact, if you think about it, where is the location of my slope, or where's the x value for it? It's 2. So to find the slope of the tangent, that's the same thing as finding what? The derivative of f at 2. Okay, so that's what I'm going after. I'm going after f prime of 2. So that would mean, by definition, it's the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h, which is equivalent to f of 2 plus h would be what? The limit as h approaches 0 of 2 plus h squared minus f of 2, which is 4, all over h. So now let's just simplify through. So the limit as h approaches 0, 2 plus h squared is what? 4 plus 4h plus h squared minus 4 all over h. And then, of course, the 4's cancel out. So now I could factor out. So now I could factor out an h from down here. And if I factor out an h, that leaves me with limit as h approaches 0. It gives me 4 plus h all over h. Cancel out the h's. Now I could use direct substitution, and if I plug in 0 for h, I get 4. So that's the slope of my tangent, which was the same thing as finding the derivative of this function at 2. So then, once I have the slope of my tangent, we have the points that the line goes through. So the equation of my line is y minus 4 equals to the slope times x minus 2. And I wrote the equation of this line in point-slope form. If you want to write it in slope-intercept after you write it in point-slope form, you could. Okay, or you could leave it that way, unless I specify how I want you to write the equation of this tangent line. Okay, so this basically wraps up this section. So just quickly, just to recap, remember the derivative. What does f prime of a represent? Well, f prime of a represents many things. It could be the slope of the tangent at x equals a, so at x equals to a, or if this function represents, or if f represents the position of a function, then this could be the velocity, and to be more specific, it's instantaneous velocity, but this is only if f is the position function. And then it also means instantaneous rate of change. So it tells you how fast your function is changing, how fast f is changing at x equals a. Okay, so these are the three things it means. And you're going to notice that basically semester 1, the best way to summarize semester 1, if you're to say, hey, Mr. Gregorian, what's one word you could use to summarize semester 1 of calculus? And I would say derivatives, because everything is tied down to derivatives. Now, we're going to do a lot of interesting things with derivatives, but that's basically where it ends. It basically ends at derivatives. Okay, so that wraps up this section.